Hello everyone, I'm with you with a new education video. It's really nice to be with you again. Today we will learn some information about the drift speed of the electron, electric field, magnetic field, and electrical energy. We will see how speed is an electron and how does a device works with electrical energy. I have prepared a video for you. After watching the video, I will explain a few more things and end this lesson. So, let's see the video. We have a circuit with three elements: a LED, a switch, and a 3-volt 1 ampere hour battery. Now we will see what happens in the circuit when we turn on the switch. The current is moving along the line, but the drift speed of the current is very slow. This means that the flow of current does not cause the LED to emit light. We call this the drift speed of the electron. For example, if a current of 20 milliamps was passing through a wire with a diameter of 1 millimeter, the electron would be able to drift a distance of 1.87 micrometers per second. This means that we would have to wait 15 hours for an LED to provide light if the position of the LED was 10 centimeters away on the wire. So, how can it provide light immediately? Electrons are very slow, but the electric field is pretty fast. In this way, we can produce electromagnetic waves and transfer energy via photons along the cable at speeds close to the speed of light. Because this electromagnetic wave is not in a vacuum, it's not at the speed of light, but it's very close to the speed of light. This is called signal rate. There are two ways to change the electric field, which is part of the fabric of the universe. Either we need to move the magnets, which is not our topic right now, or it's necessary to create a potential difference and move the charged particles. When charged particles or an electric field are moved, a magnetic field must also be created. We can find the direction of the magnetic field using the right-hand rule. When the thumb of our right hand is held to point in the direction of the current, the other fingers show the direction of the magnetic field. Electrons move from the negative pole to the positive pole, opposite the direction of the electric field. However, since the direction of current flow was initially accepted by scientists as being from the positive pole to the negative pole, it remained this way. And this is how the current direction is considered. The electron was discovered by Joseph John Thomson in 1897. The first person to say that electrons are negatively charged was Benjamin Franklin. In 1747, he said that charges were two types: negative and positive. The direction of the electron was not changed to avoid confusion. However, what activates electronic devices is not exactly the electromagnetic wave itself, but electrical energy. The amount of electrical energy transferred per unit time is called electrical power. The power transferred through the unit volume of a wire is called electrical power density. Power density appears as watt per kilogram, and it shows us how powerful the stored energy can be charged and discharged. Energy density appears as watt-hour per kilogram. It indicates how much energy you can store in each kilogram. Electrical energy or electrical power density does not flow in the direction of the cable like electrons. The direction of electrical energy is determined by a third vector called the Poynting vector. The Poynting vector describes the energy flux of an electromagnetic field. It takes its name from its inventor, John Henry Poynting. This direction should always be perpendicular to the electric field and magnetic field vectors. In other words, energy is transferring from the universe to the copper wire. Due to the law of conservation of energy, if we receive energy from the universe, we also have to give as much energy as we receive. This energy is also provided by the battery. This action occurs at the same time. So, We can turn on the light easily with the switch. Turn off and on. Turn off and on. That's all we need. The direction of electric field lines is from positive pole to the negative pole. Electric field lines start with a positive charge and are dumped with a negative charge. It starts with a positive charge and extends to infinity. It comes from infinity and ends in negative charge. As the electric field intensity increases, the lines become more frequent. Electric field lines never intersect. Electric fields can be combined due to the principle of superposition. Electric field lines created by the same charge extend parallel to each other and never touch. This is also the same type of charge. Magnetic field lines start from the North Pole and end at the South Pole. Magnetic field lines of the same type of poles don't touch each other. This is also the same type of pole. Different types of poles attract each other. This is the end of my lesson. Thanks for watching. Take care of yourself. Hope to see you again. Bye bye.